So, welcome to the PALS seminar this semester. Our first talk will be on filtered Boolean powers and their automorphism groups by Mayr.
Thank you. Yeah, very happy that people got back to this occasion. I'm going to talk about some joint work with Nick Rushkutz from the University of St. Andrews about filtered Boolean powers, their properties, and automorphism groups in particular. So a brief outline is going to be split into two halves. First, I'm going to give some talk about varieties generated by simple non-abelian Maltsev algebras and how filtered Boolean powers arise there and introduce them there. And then in the second half, I'm going to talk more generally about combinatorial properties of these filtered Boolean powers, and in particular, properties of their automorphism groups. So let's start with talking about varieties. Going back a very long time, right? So just to remind you, a finite algebra is called primal if every finitary operation on that algebra is induced by a term function, the algebra. I think people, typical examples, the Boolean algebra of size 2, also a finite field. I think people started looking at those in the 40s and 50s because they wanted to represent operations on finite sets using term operations of some algebras. So primal algebras have a very rich structure of term operations, and this has strong implications for the varieties that these algebras generate. So just a reminder, the variety V of A generated by an algebra A is just a class of homomorphic images of subalgebras of direct powers of A. So these are old results. We know that the finite members in the variety generated by primal algebra are just direct powers of that algebra A. Foster showed in the 1950s that all members of that variety are Boolean powers, A to the B for some Boolean algebra B. I'll introduce the definition for Boolean powers in a few minutes. And there's a result by Hu that shows that this correspondence between varieties generated by primal algebras and Boolean the variety of Boolean algebras is a categorical equivalence. And so these are really just very close objects. So everything more or less is known here. Let's say one can try to relax this notion of primality, and people have done that by saying a function is an algebra is functionally complete if every operation on it is induced by a polynomial function of that algebra. So now you're also allowed to plug in constants into your term functions. And classical examples for that are arbitrary finite fields, finite simple non-abelian groups. It turns out if you have a Maltsev algebra, which is functionally complete, so say any example of Maltsev algebras are groups or quasi-groups, rings, loops. For them, functional completeness just means that the algebras have to be simple and non-abelian. in the general universal algebraic sense. Now, you can ask again, what can you say about the variety generated by a functional complete algebra? In general, not much, but for functionally complete Maltsev algebras, we can get some information. The problem for these algebras is they are simple, but they may have lots of subalgebras. So if you take a simple non-abelian group, subgroups can be very wild. But if we take all the proper subalgebras of that algebra and look which variety they generate, let's call that W, then at least for the finite algebras in the variety generated by A, we have some representation. We can write them. They're all direct powers of the original algebra A with an element, a finite algebra in W. So modulo this W, at least the finite algebras in that variety are just direct powers and can be easily understood. So I want to concentrate on these finite direct powers of simple non-abelian Maltsev algebras. They are very rigid, have a very rigid structure. So this result may be folklore or maybe due to some or all of these people, Foster, Pixley, Werner. If you have a homomorphism from a direct power of A into another direct power, then this has to have a very specific form. As follows: you take so you take the k components of an element in A to the k, and just apply endomorphisms of A to every component and reassemble that to n components of A to the n. And this endomorphisms of A, since A is simple, they are all automorphisms or constants, endomorphisms to one element subalgebra of A. So this that you can split up all homomorphisms this way is just it's not hard to show, but it's just an example of how rigid these direct powers are. And if you know that, then you can see that the class of finite direct powers has amalgamation. Right? So this is almost a Freisig class. Let's just review these notions. So A is going to be a finite simple non-abelian Maltsev algebra. Let's look at K, the class of all direct powers of finite direct powers of A. It's easy to see that this class has the joint embedding property. So take two direct powers V and W of A, you can embed them into a third direct power of A. Actually, you don't need any assumptions on A for that. It's always going to work. More interestingly, like I mentioned, this class has amalgamation. So it means if you have one direct power U and any embedding into another direct power V, then another embedding into some W, then you can find a fourth direct power and embeddings from V into X and W into X, such that the composition of these embeddings on both sides yield the same, right? So that this diagram commutes. This is somewhat non-trivial and uses this particular form of homomorphisms between direct powers that I showed before. Now, Freise classes are usually also closed under substructures. This class of direct powers is not going to be in general, because a direct power may have some subalgebra which is not a direct power again, right? So except in some degenerate cases, we were not going to have this hereditary property. It's usually used to characterize Freise classes, but there is a not all is lost, right? So we have amalgamation and joint embedding, and there is a generalization of Freise's theorem that says that for such classes you can already define some. There exists some Freise limit with the following properties. So there exists a unique up to isomorphism unique countable algebra D, which I call the Freise limit of the class of finite direct powers of A, such that every finitely generated subalgebra of D is not going to be in my class, but it's going to embed into one element of my class in some direct power of A. D can be written as a direct limit of direct powers, and every isomorphism between subalgebras of A that are direct powers, sorry, subalgebras of D that are direct powers of A can be extended to an automorphism of the whole Freise limit D. So D is not homogeneous on all subalgebras, but for it's K homogeneous just for elements that are substructures that are isomorphic to elements in K. So these are the three characterizing properties of the Freise limit. And as a bonus, you see that the Freise limit is omega categorical, and it's universal for the finite elements in the class of finite elements in the variety generated by A, meaning every such finite member of that variety embeds into that Freise. So that's all.
This is all assuming that you have one of these simple, that the top line is a guiding assumption for the page. Is that
Yes,
right?
yes.
Yeah.
So all of what I said here, this just works for K being the class of finite direct power of a finite simple non-abelian Maltsev algebra. Otherwise, I do not have amalgamation and joint embedding. And this
well, just suppose you had a class with amalgamation and joint embedding, but without substructure, without being closed under substructure, but then you just closed under substructures. Is that going to work, or are you using much more about the condition?
Sorry.
Well, I mean, basically, a very naive way to think this works is you look at the hereditary class generated by the original one.
Yeah.
And then magically the amalgamation and joint embedding pass on.
That's an excellent point. That I should if you close under taking substructures, subalgebras for this class, you lose amalgamation. Right? So then you would get the class of all finite members in the variety, but this one has doesn't have amalgamation in general, and so you can't. You're not getting a Freise limit for that class, and in particular, you're not going to get some homogeneity on arbitrary substructures.
Thank you.
Is there a description of the age of this limit?
Sure. I mean, the age of that, if you think of all finitely generated substructures, it's just gonna be the finite elements of the variety generated by A.
Okay.
So that would be the classical age.
Okay.
Okay. So, well, that's all very nice if you like these kind of things, price limits, right? But it still kind of begs the question for me, naively, can we describe this price limit somewhat explicitly, except as such a direct limit of direct powers? And the answer is, of course, yes, we can. Using constructions called filtered Boolean powers. That's due to Ahrens and Kaplansky, I think. So let's let B be a Boolean algebra with corresponding stone space X. So this is just a set of the space of ultrafilters on that Boolean algebra. Then I can take an arbitrary algebra A with discrete topology, and I can look at all the continuous functions from the stone space X into A. That's going to give me a subset of functions A to the X with pointwise operations of the algebra. That's the Boolean power of A by the Boolean algebra B. And somehow historically, these things are in subalgebra of A to the X, but somehow historically, these things are denoted by A to the B. For, or similar notions. Now, I'll need to, these are what classical Boolean powers are. And now for the filtered Boolean powers, I'm going to borrow some notion from semigroup theory. I'm going to say an element E in an algebra is idempotent if and only if it generates trivial subalgebra. And now, if I pick some points x1 up to xn in my stone space and idempotence E1 to En, then in my algebra A, then I can look at all the continuous functions from X to A that map Xi to Ei for all I. And that's going to form a subalgebra of A to the X, which I'll call the filtered Boolean power. And using this notation with the xi's in the exponent, the ei's down there, so that we remember x1 has to be fixed to E1 in these functions. So now the result that was promised in the abstract for a finite simple non-abelian Maltsev algebra, this Freise limit of finite direct powers of A is isomorphic to a filtered Boolean power of A by B, where what do I have to filter by? E1 to En is the set of all idempotents of A. So a list of one-element subalgebras, if you will. B is the countable atomless Boolean algebra, specific algebra, and x1 up to xn arbitrary points in distinct points in its stone space, which is just the Cantor space. Popular thing. So right. So if you have these objects, then showing this isomorphism is easy. You just have to check that this filtered Boolean power satisfies this defining properties of the Freisel limits from the 2 slides ago, right? So it's countable. It's a direct limit of direct powers of A. What else? It's K homogeneous, so it's every isomorphism between substructures that are isomorphic with direct powers can be extended to automorphisms of the whole thing, and yeah. 2, 3. I hope I got everything right, but just following the definitions. Okay, so I want to show you another place where this filtered Boolean powers come up, namely, again, a finite simple non-abelian multiple of algebra. You can look at the free algebra of countable rank in the variety generated by A. And, let's look at, it has a sub variety, has a subvariety that's generated by all the proper subalgebras of A. And if you take the free algebra of countable rank in V, there is a minimal, unique minimal congruence theta, such that the quotient modulo theta is going to be in the subvariety W. And then it turns out every theta class, class for that congruence, which happens to be a subalgebra of the free algebra, is actually isomorphic to the filtered Boolean power that we just saw. So proof of that is not hard. It just you use an explicit representation of the free algebra in V as subalgebra of A to the N, and then identify the theta classes in there. So it looks a bit abstract. For groups, this was actually observed in the 90s by, I think, Bryant and Gross for the first time. You specialize this result to classical algebras like groups, loops, or rings, where congruences are determined by you just have one idempotent trivial subalgebra, and congruences are determined by the classes of these identity. And then you'll get we can sharpen that result and say for a finite simple non-abelian group, the free group generated of countable rank generated in the variety generated by A is a semi-direct product of a filtered Boolean power of A to the B with the free algebra in W, the variety generated by all the proper subgroups. All right, so this, I think, concludes the first part of my talk. It's probably a good place to stop and ask whether there are any questions.
I have a question on something you said earlier about someone asked about the age of this variety, and you said it's finite members of the variety. I feel like it should be SP of A rather than HSP of A. The finite members of SP of A perhaps is the H. Can you get, like, let's take a simple group that has, not even a simple group that has the quaternion group as a subgroup, right? then when you look at the age, you'll get the quaternion group, but you won't get other large subdirectly reducible groups that are generated by the quaternion group. Right? Not all the subgroups are embeddable in powers of 8.
That's right. Yeah. I think you're correct there. Yeah. Sorry about that. So I'm not sure whether people out there heard this conversation. Keith corrected me and pointed out that for the age of the this Freise limit that we're constructing here, I don't necessarily get all homomorphic images of subalgebras of direct powers, but just the subalgebras. And any other questions, comments? So then I want to pass on to the second part, talk. Hopefully, I gave you some idea that these filtered Boolean powers, they come up in natural situations. Now I want to talk about their automorphism groups and I'll start by stepping back to a bigger picture again. So let's think about M, any countable infinite structure, maybe algebraic or relational, some first order structure, say, and let G denote the automorphism group of M. And then this G is a group, and it has a natural topological structure that's called pointwise convergence sometimes, where the basic open sets for this topology are just cosets of stabilizers of finitely many points in elements in the structure M. That is what basic open sets look like, and with this topology turns out to be separable and metrizable. Can put a metric on it, which actually makes this group not just a topological group, but a Polish group. Now, a few properties that people have been studying about these automorphism groups. The first one is so-called small index property. So an algebra structure M has the small index property if every subgroup H in the automorphism group whose index is smaller than 2 to the Aleph naught is open. So that means it contains one of these guys up here, a stabilizer of finitely many points of the whole automorphism group. So this just means that if the index is small, then this subalgebra has to be big. Right? Contains an open set. Why are people interested in this condition in particular? If your structure has a small index property, then any homomorphism from the group, the automorphism group G, into another topological group will automatically be continuous. So in other words, you can recapture the topology for structures with small index property from the algebraic features of the automorphism group. We had some talks by Michael Pinsker a couple of years ago, and student Clemens Schindler about capturing or when which groups or endomorphisms, monoids, have a unique Polish topology on them. So having small index property will guarantee that. Right? So this is a property that also lately came up when studying constraint satisfaction problems on countable structures. So many useful in many different applications. I'll mention a few more. So a group has uncountable cofinality if it's not a countable union of a chain of proper subgroups. And so this is again saying something like the group is big, cannot be approximated by a countable union of proper subgroups. Group G has the Bergman property if for any generating set for the group that contains the identity and is symmetric in that it contains for every element also its inverse. For every such generating set, there exists a natural number k such that G can be written as a product of k elements from as k product of k generators. And sometimes this is also called maybe bounded with. It just means that you have a bound on the number of products that you need for generating all elements in the group. And finally, generics. So this is a property of conjugacy classes in the group G, just defined a generic element in a group G as one that has a co-meager conjugacy class. So a big conjugacy class, where big means co-meager, it means it contains the intersection of countably many dense open subsets of that group. So this is what a single generic element in a group G is. And we say a group G has ample generics if for every natural number n, we consider the conjugacy action of G on G to the n, and we can find such a co-meager orbit under this action there. Okay, so a whole lot of properties, seemingly random. There's an influential paper by Kekris and Rosenthal from 2007, where they showed that the connections between these properties, namely, if we have ample generics, and this implies a small index property and consequently uniqueness of the Polish topology on the automorphism group of the structure M. And if additionally this structure is omega categorical and you have ample generics, then you also have uncountable cofinality and the Bergman property for the automorphism group. So, okay, then there has been in model theory, I guess, and topological dynamics and other constraint satisfaction. There's been a whole industry of showing, looking at homogeneous structures or omega category structures and trying to figure out which of those have these properties. So just have a small sample of results for you here. It's probably not worthwhile to go through all of that. I may just mention, if you take just a set, countable set N, the automorphism group is the symmetric group, right? And people in the 80s showed small index and uncountable cofinality for the symmetric group on the countable infinite set. And then 2006, Bergman's paper appeared where he showed a Bergman property for the symmetric group. And soon afterwards, Kekris and Rosendahl developed their notion of ample generics, building on some work by Hodges, and Lasker and Gillard from the 90s, and showed that those connections between these properties. So, of course, their result that this symmetric group has ample generics implies all the previous ones. A random graph has all these nice properties. Maybe it's worthwhile to point out that if you take the rationals with less than or equals or dense linear order, it has small index property, uncountable cofinality, and the Bergman property, but it does not have ample generics. So it has it's missing a generic. It has a generic element for G acting on itself, but not for G acting on G squared. Then most of these results were shown for relational structures, but in the 90s, Bryant and Evans investigated the free group of countable rank in the variety of all groups, and showed that they have that the automorphism group has small index property, uncountable cofinality, and also something like ample generics, which turned out to be the notion that Kekris and Rosendahl used later. For us, it's going to be important. The counter space or the countable atomless Boolean algebra has all these nice properties. And what's our contribution now? It's at the very last row. If A is a finite simple non-abelian Maltsev algebra, B countable atomless Boolean algebra, then any filtered Boolean power like this is going to have small index, uncountable cofinality, and Bergman property. We do not know about whether it has ample generics. So let's see whether I can give you just some ideas for went into the proofs of these results. Maybe one thing that's worth mentioning is also these filtered Boolean powers that we are looking at here. They are all omega categorical. Just briefly, this follows by work of McIntyre and Rosenstein from the 70s, where they investigated that question, gave criteria for when Boolean filtered Boolean powers omega categorical. So essentially, you have to check that if you filter by points x1 up to xn, so these ultra filters of the Boolean algebra, you can think of your Boolean algebra B expanded with these ultra filters as unary relations. And this structure you can check with their criterion turns out to be omega categorical, and then from this it follows that this filtered Boolean power is going to be omega categorical as well. Just to point out in this table here, all my examples are omega categorical also, except for this free group of countable rank. So this is somewhat an outlier in the results as well. I'm gonna skip congruences, but maybe I'll talk about the structure of the automorphism groups of these filtered Boolean powers. Recall that the automorphisms of Boolean algebra correspond to homeomorphisms, continuous bijections of its Stone space. And we'll denote the homeomorphisms, set of group of homeomorphisms by homeo x. And then we can show that if we have a finite simple non-abelian Maltsev algebra, B a countable atomless Boolean algebra, X the Cantor space, then such a filtered, the automorphism group of such a filtered Boolean power splits into a semi-direct product of some normal subgroup, and with the homeomorphisms of X that fix all these filter points x1 up to xn that we are using. And we can also describe this normal subgroup. It's something like the closure of a filtered Boolean power of the automorphism group of A by B. But then that's not big enough. You have to take the closure of that group inside the whole automorphism to get this normal subgroup then. Okay, so what's the as an algebraist, right? I'm always happy if I get this semi-direct decompositions. It's the big takeaway here. The automorphism group of a filtered Boolean power is a semi-direct product of something with the homeomorphisms, stabilizer of homeomorphism group. And now, if we want to prove the small index property, say for a filtered Boolean power, then we want to prove the small index property for this complement, the subgroup first, as a first step. So actually, this is a generalization of a result by Truss from the 80s, where he showed that the automorphism group of the countable atomless Boolean algebra, or the homeomorphism group of the Cantor space, has a small index, the small index property. Now we just need to follow his proof ideas and show the same thing for a stabilizer of this homeomorphism group. And the way this is done by just looking at homeomorphisms, something like the punctured Cantor space, where we remove the points x1 up to xn that we want to filter by, look at the homeomorphisms of this space and somehow patch them together in order to show what we want, that we get this small index property. And so it was really it's a bit annoying. That it took some heroic effort of Nick, who fought it out with these patching up these homeomorphisms to get this result for the stabilizer of finitely many points in the homomorphism group. Once you have that, and you have this decomposition of the automorphism group of a filtered Boolean power, semi-direct decomposition, you can kind of bootstrap from there to show if the complement has the small index property, to get the small index property for the automorphism group of the whole automorphism group. So I'm not gonna go into details for that. And so the story for uncountable cofinality and the Bergman property is similar. We show these properties essentially for the stabilizer of finitely many points in the homomorphism group of the Cantor space. It's even worse than what we need to do for the small index property. You need to prove things like some homomorphisms of this punctured space can be written as a product of 8 conjugates of other homomorphisms that have certain properties. But again, Nick pushed through that, right? And if you have this result for the stabilizer, then it's less than superhuman effort to extend it to the filtered Boolean power, the automorphism group of the filtered Boolean power, to show that you have what's called uncountable strong cofinality, which is actually equivalent to uncountable cofinality and Bergman property at the same time. So that's it on results. I think I may have 1 minute still in the talk. So I'd like to leave you with some open questions that came out of this. So let's have A be a finite simple non-abelian Markov algebra, or just a group, if you want. Then first question is every group in the variety generated by A an extension of the filtered Boolean power of A by some group that's in the variety generated by proper subgroups of A. So we showed that this is true for the free group of countable rank in that variety, and hence it follows for all countable groups as well. But for larger cardinalities, we don't know. Second, there's an old question by Bryant and Evans from the 90s. You can look at the free group of countable rank in the variety generated by A. They wanted to know whether this group has the small index property. So you have to study the automorphism group of this free group of countable rank and show look at small index subgroups there. This is still open. We know that this filtered Boolean power sits inside that free group of countable rank, but yeah, So this doesn't seem to be a way how to bootstrap this result to the whole free group.
I have a question. A is a group here, is that right?
Yeah, let's assume.
Okay. But if you have three groups of countable rank, can't you just take subgroups generated by first generator, then generated by first two, then generated by first three? That's a countable chain.
Yeah. So you have a countable chain that gives you, whose union gives you the free group of countable rank.
Right?
But I want to do that for the automorphism group of the
Okay,
free group
yeah,
of countable rank. Right?
okay.
Yeah. And finally, so we showed that this filtered Boolean power has of A by the countable atomless Boolean algebra has a small index property and uncountable cofinality and Bergman property, right? But we still do not know whether it has ample generics, which would subsume all the other three results. Yeah, so unclear how to get that. Right, I think that's all my time. Thanks for listening.
Yeah, so thank you very much, Peter.
Well,